We now want to talk about our two conservation laws, Kirchoff's voltage law and Kirchoff's current law. So first, Kirchoff's current law is a statement about the conservation of charge. Okay, just like we have conservation of mass, no mass is created or destroyed. We have conservation of charge, no charge is created or destroyed. And so in an electric circuit where current or charge is moving around, if we pick any point, an intersection if you will, where charge is arriving and charge is leaving, then if we sum all of the charges that are entering and those that are leaving, it must all sum to zero. In other words, what the charge or the current, which is charge per unit time, entering a node must equal the current or charge per unit time leaving the node. And so this is nothing more than just saying that if you sum all of the currents that are labeled as entering a node, then they will be equal to zero. If you sum all of the currents labeled as leaving a node, they will equal zero as well. So as an example, here we have a circuit or a node only with four currents, IA through ID, and you see the arrow convention there. And so we're going to sum, I'm going to choose to sum the currents that are entering the node in this case. So I've got IA that enters, I've got IB that enters, and because IC is pointing away, we have minus IC entering and we have minus ID entering. And those all added together should add up to zero according to Kirchoff's current law. And we can write that in short form here, I guess, by just using a summation form. I sub n, the sum of I sub n over n equal 1 to capital N, where capital N is the number of branches that are connecting to a particular node. That summation must equal 0. Okay, so let's just look at an example or two here. So let's find the current I if the voltage source supplies 3 amps. So if the voltage source supplies 3 amps, and I've got 3 amps this way. Supplying means it's coming from its positive terminal. So I need to write a Kcl equation for this node right here. Okay, and I will go ahead and rewrite it. We'll sum currents leaving the node, okay? Leaving. So we have 2 amps leaving down through R2. We have I current leaving through R3. We have minus 5 amps that is leaving from the 5 amp source. And from the voltage source, we have minus 3 amps leaving, right? Because it's actually entering. So you sum those up. We'll solve for I by bringing all those currents to the right. So that means 8 minus 2, or 6 amps. Okay. In the second example, we're told that Ix is equal to 3 amps. And the 18-volt source delivers 8 amps. So again, if it's delivering, it's going to come from its positive terminal. And the question is, find RA. Well, to find RA, this is a little bit more than just KCL, right? I've got a voltage here. I'll call it VA. And I've got a current, IA. Okay, so I'm just going to start with the real basics here, right? If there's an RA, then by Ohm's law, I can say that that resistance is VA over IA. So what I need to find out is I need to find V and I. Well, it just so happens that that resistor is in parallel with an 18-volt source. So that means, because they're in parallel, actually by KVL, which we haven't looked at yet, the voltage VA is going to be just 18 volts. So what I really need to find is just IA. So how can I find IA? Well, we can just write a Kcl equation for this node up here. I think we have all the other currents identified. So let's do that. We have, if I sum currents leaving that node, I'll do currents entering. Let's just do entering for fun this time. So entering the node, we'll have 8 amps entering. We have 13 amps entering from the right. We have minus 3 amps leaving through the 6 ohms, or entering, minus 3 amps entering, and we have minus IA entering. Right? So that means IA is equal to 13 plus 8 is 21 minus 3 is 18. And so that means that this resistance is 1 ohm, 18 volts over 18 amps. Okay, now moving on to the second conservation law. It's actually a conservation of energy. Kirchoff's voltage law. Kirchoff's voltage law is a conservation really of energy. And what it says is that if you have a loop, any loop in a circuit, so we defined already what a loop is, but it's a path, and a path is just a connected set of branches. So you're going through a number of branches, and the last node that you arrive at is the same node that you started with. So that's a loop, a closed path. You walk around any closed path, adding all the voltages of the branches that you cross to complete that loop, and those voltages must add up to 0. And in doing so, if that is the case, you're conserving energy. If that were not the case, then you could not conserve energy. So, for example, look at this circuit right here. Let's say that we put a little test charge dq. All right, let's say that it was actually 1 coulomb. And we were down at node 1. And we said that VA, let's say, was 4 volts. Okay, if it's 4 volts, that's actually 4 joules per coulomb. So if we move that 1 coulomb from node 1 up to node 2, it's going to take 4 joules of energy to move that charge up that potential, right? Because it's a 4 joule per coulomb potential. If we said, well, hey, I think that VB is 5 volts, okay, 5 joules per coulomb. Well, that's handy, because now if we have that test charge dq up here, 1 coulomb, and now it comes back down to where it started from, because it now traversed a branch that actually had 5 volts across it, that 1 coulomb could actually do 5 joules of work. It gives up 5 joules. So that means we need to put 4 joules in, but we get 5 joules out. Right? So we don't have conservation of energy, and we actually have a perpetual motion machine. Even better than that, we can have some free energy. Okay, so that's what's behind, or that's why we say conservation of energy is really what KCL is about. KCL is very analogous to when you do free body diagram mechanics, static problems where you're looking at all the forces on some body and you sum all those forces to 0. It's very analogous to that. Let's look in closing at 2 examples. Okay. So the first one is find Vx and Ix. Well, we're going to, clearly, because we're studying KVL, we're going to use KVL. We've got a loop, right? And we're going to walk around the loop here. It's not probably necessary to do this, but we're going to exercise our KVL this time. And when you do KVL, you start anywhere in the loop and you go around. I typically start in the bottom left corner, and I typically go clockwise. But you can choose your own convention. Anything will do. So the other thing I choose is that whenever I encounter a minus sign, I actually will say I've just had a minus voltage. Okay, even though if you think of it, the potential at this node here, at the positive end of the 5 volt source, is 5 volts more positive than it is at this end. So you could say, well, every time I encounter a negative sign, I'm actually going to add, in this case, 5 volts. And that's fine. But I'm choosing the convention that whenever I encounter a negative sign, I'll put minus. So here we go. We'll start at the bottom left corner, and we walk around clockwise. So I encounter the negative sign, so I have minus 5 volts. Then on to the 7-volt source, I encounter the negative sign, so it's minus 7 volts. And then finally, we encounter the resistor, which has a voltage already labeled across it. And the polarity there is plus to minus, so we'll add Vx. And all of that must equal to 0. We can now solve for Vx by simply pulling 5 and 7 over to the other side, and we have Vx equal to 12. Lastly, we can find the current Ix by just applying Ohm's law, which is Vx over our 100 ohms. And so we'll have 120 milliamps, or 0.12 amps. Okay, let's look at this next example. Here we're asked to find VR2, that's this voltage here, and as well as Vx, which is right here. Okay. So there are actually 2 loops here. All right, and we can write a KVL equation around both of them. I think there's a little cutoff. I think that's 4 volts, if I recall. Yes. Now, let's do KVL around the left loop here. So KVL, and I'll call this M1 and I'll call this M2. M stands for mesh. Those are actually meshes. Remember, meshes are loops that don't have any loops inside them. So if we do KVL at mesh 1, okay, so that'll be my notation. Start in the bottom left-hand corner, I get plus 4. Then I encounter the minus sign of the 36-volt source, and then I encounter the positive sign of VR2. That's equal to 0. That tells me VR2 is equal to 36 minus 4, or 32 volts. Okay, now we can do KVL at M2 around the second mesh. I'm going to have minus VR2, but I know what that is. That's 32 volts. Okay, we can go ahead and write that. We then encounter plus 12 volts for that resistor, plus 14 volts for that blob. We get minus V2 for the other blob. We get minus VS1, and we get plus VR1, and that is equal to 0. Now it turns out that to answer the question, I don't have to write the KVL of the second loop, as I did actually, but I should have written a different KVL equation, but we got to practice KVL anyway. Let's go back and let me show you, kind of draw this another way here. If I draw like a box here, now let me undo that. Let me draw the box here. Let's say this was some kind of another component, right? Just like these were blob, just like this blob here, that's another component, and it has a voltage Vx. Now true, this Vx is made up of other voltages inside. However, I'm being asked in this problem just to find Vx. So I can go around this loop here, call it M2, and yes, I could, as I did just a minute ago, I could go around the loop and include minus V2, minus VS1, plus VR1, or I could replace all of those right here with just Vx. Can I not? Right? I can, because that's labeled from node A to node B, which spans those 3 elements. There's, someone has labeled those Vx, and that's what I'm asked to find. So with that, I can actually now use this second KVL equation to solve for Vx. So Vx is equal to, and I've got to pull my 32 volts to the other side, minus 12 volts minus 14. And that leaves me with 20 minus 14, or 6 volts for Vx. Now there's one more problem here. Let's see. Sorry, my computer is very slow right now. Okay, in this last one, it's finding Vx, which is this voltage across this current source. And what we need to do in this case is we need to determine ultimately, this is kind of indirect. You've got to think a little bit more on this. I'll let you work through it. The solution is right in front of you, but the idea is this, that I'd like to know the voltages across all of these elements, right? Like if I knew this voltage, and if I knew this voltage here, right, then I could actually write what Vx was. Let me label this V8, that voltage, and let me call this V4. Then I could write a KVL equation that goes through the 60 volt source, the 8 ohm resistor, the 4 ohm resistor, and then back around through Vx, right? I can do that, and I will do that right now. So I would have minus 60 volts plus V8 plus V4 and then plus Vx is equal to 0. And I can write that Vx then is equal to 60 volts minus V4 minus V8. And the question now is, what is V4 and what is V8? Well, you just use some Ohm's law. For instance, V8 is simply 5 amps times 8 ohms, or 40 volts, right? Because we're given that there's 5 amps that's flowing through that 8 ohms. Now, we're not told what I4 is, and I'll let you figure this out. However, once you know that there's 40 volts across V8, you now can determine the voltage across this 10 ohm resistor. Call it V10. V10 now is equal to 60 volts minus 40 volts, which is 20 volts. So we know there's 20 volts across this 10 ohm resistor. From that you can determine how much current is flowing through the 10 ohm resistor. And then you use KCl at this node to say, okay, if I've got 5 amps entering from the left and I've got some amount of current that you will calculate leaving, going down through the 10 ohms, that leaves some amount of the 5 amps to go through the 4 ohm resistor. And with that current and the 4 ohm value, you can calculate V4. And once you have V4, you can calculate Vx.